In example 3.4, we have this box that goes to infinity on both the positive and z direction, and with two grounded plates on the bottom and top that I used green for, which have V is equals to 0, so on top and on the bottom. And then on the two sides instead, we're going to have the V naught. These two plates are kept at a certain charge, a certain voltage. So we can find out the boundary condition. We know that V is equals to 0 in our case when we are on the bottom plate. So when y is equals to 0, we know the V is equals to 0 when y is equals to a, of course, because of the other top plate, and then we know the B is equals to V naught when x is equals to b, and b is equals to v naught when x is equals to negative b. And we have these four boundary conditions. We have nothing on the z because we know it's infinite along those lines, and there is no parallel. So one thing that you can notice is that we have two couple. The first one talks about the y direction. The second one talks about the x direction. So we know that our problem will be in two dimensions. So our Laplace equation will be a Laplace equation in two dimensions. So if we go a little faster on the detailed, if you need more details, you can watch the previous video. We can say that our capital X, in terms of X, double prime is equals to k squared times capital X in terms of X. So if we solve the second differential equation, second order differential equation, we're going to have the r squared is equals to k squared, so r is equals to plus or minus k. Instead, for the y, in terms of y double prime, is going to be equals to negative k squared y in terms of y. So if we solve this one, we get r squared is equals to negative k squared. So r is equals to ik. Okay? So the first part will be equals to a e to the power of kx plus b e to the power of negative kx. The second one, since we have an I, we're going to have c cosine of ky plus d sine of ky. And we know that our voltage potential depends both on x and y. So it's going to be equals to the first part times the second part. Okay. And now we can start plugging in the boundary condition. So we know that when y is equals to 0, our voltage has to be equals to 0. So if we take this and we plug in y is equals to 0, so let me copy it, it's over here, for the first boundary condition. Oops. We're going to have the y is equals to 0, so we just substitute every single thing with y is equals to 0. So we can say that the first a and b don't really care about whether y is equal to 0 or not. And we know that this has to be equal to 0. And we know the cosine of 0 is equals to 1, and sine of 0 is equals to 0. So here we will get this part which says the same times c. Is equals to 0. The only way we can get 0 if c is equals to 0. So that means that if we rewrite our equation after the boundary condition, the first boundary condition, actually let me take the problem over here, and we know that c is equal to 0, we can cancel out this term. Okay? So now our second boundary condition is that b is equal to 0 when y is equal to a. So let's go back. And we have to plug in that when y is equal to 0, our voltage has to be equal to, so when y is equal to a, our voltage has to be equal to 0. So let's take this, duplicate it. Instead of y, we're going to put a. And so the only way we can make it is by having this part equals to 0. And we know that d, well, d is, I'm going to talk about it, let's avoid talking about d right now. So we know that the only way is to have sine of k a is equals to 0. So k a has to be equals to a certain n times pi, which is then going to be equals with n, equals to 1, 2, 3, and so on. So k in our case is going to be equals to n pi over a. So that is another thing that we get out of this equation. So if we go back, copy this, paste it, copy and paste it here, and we substitute our k with n pi over a, then we know that it's going to be equals to pi over a times y. And of course we can substitute our k in the first part too, so n pi over a, and here again n pi over a. Okay, so now this is the formula that we get from the first two boundary conditions. What we get out of the third boundary condition, actually one thing is that we know this is the formula we get out of the boundary condition. That is all we know about when b is equal to 0. So once we finish when b is equal to 0, our actual solution will look a little different from this. It will be equal to something a little different. So first of all, I can identify this part right here, and say that it's actually equals to 2 hyperbolic cosine of n pi over a x. So I can rewrite this as 2 hyperbolic cosine of n pi over a x times d times sine of n pi over a y. As you can see though, we have two constants, the 2 and d. So since we're finding a general solution, we can take this and basically write them together. So our solution will be something like b, in terms of x and y, of course, equals to the sum, put another sum, of course, from with n being going from 0 to infinity. Of I'm starting from 1, of course. Of we said hyperbolic cosine base of, I'm gonna write it as n pi a over times x times sine of course, a constant in front, I'll call cn, sine of n pi a over y times y over a times y. Okay, now we have to find the value for this cn. So we know the cn is actually going to be equals to the integral from 0 to a. Actually, it would be equals to 2 over a times the integral 2 over a, because it's the period is a and it's always 2 over the period. Another period is a because it's a minus 0. So their function at that point is going to be equal to 0, b naught, because when x equals to b, our function equals to b naught, times the function that we had before, so it's this part over here, with, of course, x being equals to b, like we said. Now, as you can see, this part here is a constant, so we can take it out of the equation. So we know that cn is equals to 2 over a b naught cosine, hyperbolic cosine, of n pi over a times b. The integral from 0 to a of sine of n pi over a times y. Okay, so if we integrate this, the first part is going to be the same always, and we get a cosine actually, sorry. In front, I would have to take out a over n pi, of course, that's in front of this, cosine of n pi a over our y, times our y, sorry, from a to 0. So if we plug it back in our equation that we have, we're going to have the same part at the beginning, of course. Actually, let me simplify something. The a we can get rid of, and so we have something a little different. We're going to have 2 d naught over n pi hyperbolic cosine of n pi a over b. And the integral of this, which is then going to be equal to well, cosine of these two values. So cosine of n pi over a times a minus cosine of n pi over a times 0. Okay, so these two values cancel each other out, and this part here is simply going to be equal to 1. So what we get out of this is this exact value. So cosine of n pi minus 1. And one thing you can notice is that we're going to have actually two different answers based on if y is equals to y is going to be an even or odd function. So we're going to have here I forgot a negative in front sign when I integrated the cosine. I'm going to put it in front of everything. Okay, so if I have, for example, n being a even value, then cosine and h will be equals to 1, which then will be minus 1, which is equals to 0. So the whole thing will become 0. And then if it's instead, we have, there we go, our function to be equals to the n instead is an odd value, then we're going to find out that our actual answer is going to be equals to 4 b naught over n pi. Now I divide both sides by this value over here, so I can just bring to the other side, and therefore, if I solve it, if I basically plug in my initial equation, I'm gonna have that d x y. Oh, okay. And is equals to what we said. It's 0. It's 0 if it's an even value, so we're just going to take odd values. So 1, 3, 5, so on to infinite. Now, if we plug in what we found before, which would be, well, actually this part here will be equals to c n. So I can divide both sides by this. So I'm just going to move it to the other side. As you can see, divide both sides by this. So we get that this is our answer. Okay, so if we plug it back in, I'm going to find that I get 4 d naught over pi and n pi, actually, yes, that's correct. So n pi times cosine of this part here, we said, of course, cosine of hyperbolic of n pi a times x over, we said, cn divided by this part here. So we're going to divide it by the same part here. So I copy and paste it over here. Times the sine that we have right here. So as you can see, I just plugged in cn. Now we can do one more step, and we can see that this part here is actually constant, and we can take it out of the sum. So it's going to be equal to the sum n equals 1, 3, 5, so infinite. Sorry, let's take it out. So 4 b naught over pi 1 over
and hyperbolic cosine of n pi over ax over hyperbolic cosine of n pi over a times b sine of n pi over a times y.
And that is our final solution to our problem. As you can see, it all works out, I would say, for the best in this point.